welcome to another module in this massive open online course. Today let us take a look at a different modulation scheme, that is quadrature carrier multiplexing. Alright. So, we want to start looking at quadrature carrier multiplexing. That is QCM. Now, for this purpose, consider the two carriers consider the carrier signals. Let us consider the following two carrier signals, that is cosine 2 pi fct, which is the standard carrier signal at carrier frequency fc, and also now sine 2 pi fct. So, these are our two carriers, that is cosine 2 pi fct and sine 2 pi fct, and fc as usual is the carrier frequency. Now, observe that the phase difference between these two carriers is 90 degrees. That is, if you look at sine of 2 pi fct plus pi by 2, that is equal to cosine 2 pi fct. Therefore, these two carriers, therefore, phase difference between these two carriers is 90 degrees, or basically pi by 2 radians is pi by 2, and hence these carriers are termed to be in quadrature. Quadrature denotes a phase, quadrature basically denotes 90 degrees or a phase of pi by 2. Hence, these two carriers, that is the cosine 2 pi fct and the sine 2 pi fct, are said to be in quadrature. Hence, the two carriers that is cosine 2 pi fct and sine 2 pi fct, these are said to be in quadrature. These two carriers, cosine 2 pi fct, sine 2 pi fct, since the phase difference between them is pi by 2, these two carriers are said to be in quadrature. Now, let us consider a modulated signal xt, which is given as follows. All right. So, we have xt, consider the modulated signal xt given as consider the modulated signal xt equals, xt is given as follows, xt is equal to AC MIT, or we can just write this as AC MIT cosine 2 pi f c t minus a c m q t sine 2 pi f c t. This is our modulated signal. Now, look at this, there are two message signals in the above modulated signal. Previously, we have considered only one message signal MT. Now, there are two message signals, namely MIT and MQT. MIT is the message on the cosine. So, we have MIT and MQT. Observe MIT is the message which is modulated, message which is modulated on the cosine carrier cosine 2 pi f c t. This is also termed as the in phase carrier. This cosine carrier is also termed as the in phase carrier. The cosine carrier is also termed as the in phase carrier. So, MIT, where the I subscript I stands for in phase, correct. The subscript I stands for in phase, correct. So, MIT, there are two messages AC MIT in the modulated signal XT, which is AC MIT cosine 2 pi f c t minus AC MQT sine 2 pi f c t. There are two messages MIT and MQT. We are saying MIT is a message that is transmitted on the cosine carrier, which is also termed as the in phase carrier, and MQT simultaneously, similarly MQT MQT is the message transmitted on the quadrature on sine 2 pi f c t, which is also termed as a quadrature carrier. Remember, because sine 2 pi f c t is in quadrature with cosine 2 pi f c t. So, this is also termed as the quadrature carrier. So, this Q subscript Q stands for the term quadrature. So, we have two message signals MIT, MQT. MIT is the message signal, that is the in phase message signal transmitted on the in phase carrier cosine 2 pi f c t. MQT is the quadrature message signal transmitted on the quadrature carrier sine 2 pi f c t. Alright. So, we have two messages, remember, multiplexed on two quadrature carriers. So, implies net we have two messages which are multiplexed, correct, that is simultaneously transmitted on quadrature carriers. We have two messages which are multiplexed on quadrature carriers, hence this scheme is termed as quadrature carrier multiplexing. This scheme is termed as quadrature carrier multiplexing, which is abbreviated as QCM. This scheme where we are transmitting two message signals, different message signals MIT, MQT on quadrature carriers is termed as quadrature carrier multiplexing. Further, notice an interesting property of these quadrature carriers. notice an interesting, consider now for instance let us say we multiply or demodulate cosine 2 pi f c t by sine 2 pi f c t, that is we are multiplying at the receiver by sine 2 pi f c t, demodulating cosine 2 pi f c t by sine 2 pi f c t, that gives half sine 4 pi f c t, which is basically at 2 times the carrier frequency 2 f c. Therefore, if I low pass filter this LPF, if I pass it through the low pass filter, the resulting output equal to 0. So, if I demodulate the cosine with the sine or sine with cosine, alright, you can see that it works either way. So, cosine 2 pi f c t into sine 2 pi f c t is half sine 4 pi f c t, right, which is the component which is basically at 2 f c, which is at twice the carrier frequency. So, if I pass it through a low pass filter which is basically which has cut off frequency in the base band, then obviously the output of the low pass filter is going to be 0. Therefore, these two carriers, the cosine 2 pi f c t and sine 2 pi f c t are orthogonal, because if you demodulate cosine with sine or sine with cosine and low pass filter it, the output is 0. Therefore, the cosine and sine 2 pi f c t, therefore, these two carriers cosine 2 pi f c t cosine 2 pi f c t comma sine 2 pi f c t, these two carriers are orthogonal. This is an important property these are orthogonal carriers. Now, this property can be used for demodulation of, or this property can be used to demodulation or recover this property, that is orthogonality, can be used to recover MIT comma MQT at the receiver. So, we recover the two message signals, the in phase message signal MIT and the quadrature message signal MQT at the receiver using this orthogonality property of the carriers. Now, how is that done? Let us illustrate that at the receiver. For instance, consider demodulation with cosine 2 pi f c t. If you demodulate with cosine 2 pi f c t, what we have your x t into cosine 2 pi f c t, which is equal to a c, or let me write it a c MIT cosine 2 pi f c t minus a c MQT sine 2 pi f c t into cosine 2 pi f c t, which is equal to, now look at this, a c MIT cosine square 2 pi f c t, first term is a c MIT cosine square 2 pi f c t, which I can write as a c MIT divided by 2 into 1 plus cosine 4 pi f c t minus AC MQT sine 2 pi FCT, which I can write as AC MQT divided by 2, AC MQT divided by 2 into 2 sine into AC MQT divided by 2 into 2 sine 2 pi FCT cosine 2 pi FCT, which is sine 4 pi FCT. Okay. And now what I am going to do, just simplify this a little bit. This is basically AC MIT divided by plus AC MIT divided by 2 cosine 4 pi FCT minus AC MQT divided by 2 AC MQT divided by 2 sine 4 pi FCT. And now if you look at this, you will realize that these two, the last two components, that is AC MIT by 2 cosine 4 pi FCT and minus AC MQT divided by 2 sine 4 pi FCT, these two components are at 2 FC, alright. So, twice the carrier frequency. So, this is at 2 FC, this is at 2 FC. Of course, this is the baseband component. AC MI by 2 is simply MIT scaled by a constant. So, this is your baseband component, which is centered at 0 frequency, correct. Let me just, this is your baseband . So, if I pass this through a low pass filter, I pass this through a low pass filter of appropriate cutoff frequency, low pass filter, that is basically I low pass filter this. The components at 2 FC are filtered away, and what I have is AC MI T by 2, that is recover the in phase signal. That is what I am able to do, is I am able to recover the in phase signal. And you can see that this is possible because of the orthogonality, because once I demodulate with cosine 2 pi FCT at the receiver, the sine carrier, which is orthogonal, right, the sine carrier is orthogonal to cosine 2 pi FCT, the cosine carrier, therefore, the component, that is MQT sine 2 pi FCT, when it is demodulated with the cosine carrier, that vanishes, alright, and therefore, I am able to recover the in phase message signal. Now, similarly, to recover the quadrature message signal, obviously, I am going to demodulate with the sine 2 pi FCT, alright, and the in phase component, which is on cosine 2 pi FCT, is going to vanish, because this is orthogonal to the quadrature carrier, that is sine 2 pi FCT. Therefore, to recover MQT, let me illustrate that also briefly. Demodulate with sine 2 pi FCT, and when I demodulate with sine 2 pi FCT, I have xt sine 2 pi FCT, which is equal to AC MIT cosine 2 pi FCT minus AC MIT sine 2 pi FCT times sine 2 pi FCT, or let us demodulate with minus sine 2 pi FCT, is simply a phase changed version of sine 2 pi FCT. Okay. demodulating it with minus sin 2 pi FCT. Now, the first term is minus AC MIT by 2 cosine 2 pi FCT into sin 2 pi or 2 minus AC MIT by 2 into 2 cosine 2 pi FCT sin 2 pi FCT, which is sin 4 pi FCT, correct. Now, minus or plus AC MQT by 2 into AC MQT by 2 AC MQT into sin square AC MQT into sin square 2 pi FCT, which is basically 1 minus cosine 4 pi FCT divided by cosine 4 pi FCT divided by 2. Again simplifying this, this is going to be minus AC MIT divided by 2 divided by 2 sin 4 pi FCT plus AC MQT divided by 2, correct, minus AC MQT divided by 2 cosine 4 pi FCT. And now, if you can look at this, this component is at 2 FC, this component is at 2 FC, this is your baseband component. So, once I low pass filter this, again the components at 2 FC they go away, and what I am left with is, now I am left with this quadrature message signal AC MQT by 2. So, I am basically able to recover the quadrature message signal by. So, what we are doing is by demodulating with each of the two orthogonal subcarriers. By the cosine carrier, I am able to recover the in phase message signal. By the quadrature carrier, demodulating with the quadrature carrier, there is sin 2 pi FCT, I am able to recover the quadrature message signal. And the property that we are using essentially is that these two carriers, the cosine 2 pi FCT and sin 2 pi FCT, which are quadrature carriers, are orthogonal, alright. So, that is the important, and therefore, we are able to multiplex two signals in parallel, right, MIT, MQT, the in phase message signal and the quadrature message signal respectively on these two carriers, quadrature carriers, which are orthogonal, and this is basically termed as quadrature carrier multiplexing. Okay. So, therefore, to summarize this, therefore, using orthogonal carriers, to summarize the idea, using orthogonal carriers, that is cosine 2 pi FCT, comma sin 2 pi FCT, two parallel streams of information or two parallel message signals. And these two parallel message signals are MIT comma MQT can be transmitted on the same, and that is important, we are able to transmit on the same channel, meaning the same, sharing the same bandwidth. What we mean by this, we are transmitting them on the same channel, is that basically they are sharing the same sharing the same bandwidth, and this phenomenon, this is termed as basically, this principle or this scheme is termed as, and we have seen this before, this scheme is termed as quadrature. Quadrature carrier multiplexing, or basically quadrature carrier multiplexing, or basically QCM. So, what we have demonstrated in this module is how to use these two quadrature carriers cosine 2 pi f c t, cosine 2 pi f c t, which are orthogonal, to multiplex two different message signal, that is the in phase message signal and the quadrature message signal simultaneously on these two quadrature carriers which are orthogonal, and use this orthogonality property at the receiver to recover both the in phase message signal and the quadrature message signal by alternatively demodulating first with cosine 2 pi f c t and later with sine 2 pi f c t. Thank you. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.